Okay, polynomials with complex zeros. When we're dealing with polynomials with complex zeros, really, we're still just finding the zeros or the x-intercepts. Okay, those are the same thing. Okay, so if we're dealing with a function 3x to the fourth power, 5x cubed, 25x squared, 45x, and a minus 18. We're going to find the zeros of that. We're going to do a lot of the same process that we did in section 5.2, which you can do your P over Q list. That could be helpful, but we also want to graph that to see where it's going to cross the x-axis, and that's going to help us know about multiplicities, and it's going to help us know, okay, where do I even start with this thing? So the first thing that I would do is graph that and see what's going on with it. So let's graph that polynomial. Three x to the fourth, 5x to the third, 25x squared, 45x, minus 18. Yeah, I put a minus 1 instead of 18. Let me fix that. That's not what your graph should look like. I didn't get the 8 typed in. Come on. Okay, there we go. Definitely make sure you type it in right, because if you don't, you're going to do this. 18. All right, 8. All right, now then. Okay. We should see it crossing the x-axis a couple of places. See a nice place right there. Looks like maybe -2, hopefully. Okay, so that when I see that, I'm like, oh, I'm going to use that as one of my numbers in synthetic division. I'm going to use -2. Now, this right here is a little bit more difficult to guess at what it is. I mean, it's not quite halfway, so maybe it's 1/4, but maybe it's not, depending on what my P over Q list has. So that's where we'll go back to that list. But that one right there with -2, I'm going to verify that it works. I'm just going to trace -2, make sure it gets me 0 for y. If it does, then I know that works, and I'm going to use that in synthetic division. Okay, so that's the first thing you want to do. Three, 5, 25, 45, -18. Got a representative fourth cubed squared plane, no x's. All right, and then just run that through with synthetic. -54, -9, +18, and there's that 0 remainder that I need. Okay. The next thing that I want to do, that breaks it down from a 4th degree polynomial to this blue line now is what degree? 3rd. So every time we do synthetic, it's going to take it down 1 degree. We want to take it down until we get a quadratic. And then we can use quadratic formula, we can use factoring, a lot of things to help us there. Okay, so we want to take this down one more stage to get it down to x squared. And then we got a lot of tools that we can use. So we need to know what that place is on that. So if I think about my P over Q list, the P over Q list is really helpful when it doesn't cross at a nice number on the x-axis. That -2 is a really good number, but that other one that we saw, we know there's a 0 right there because it's crossing the x-axis. But the question is that what number is that? Because it's in between 0 and +1. Okay, so if I think about my P over Q list, I'm going to have plus or minus the factors of 18, which would be 1, 2, 3, 6, 9, and 18, divided by the factors of 3. So when I look at that, the fraction options that I've got for the P over Q list, I've got 1 over 1, 1 over 3. I've got 2 over 1 and 2 over 3. I've got 3 over 3. Well, that's 1, and then 6 over 3 is 2. 9 over 3 is 3. 18 over 3 is 6. So those are all taken care of. The rest of them are just the 1, 2, 3, 6, 9, 8, 10. That's my P over Q list. So when I look at that, it makes it more obvious what that number is when I look at that graph. It's closer to 0 than it is to 1, right? Well, which one is closer to 0? 1/3 or 2/3? 1/3. So I'm pretty sure that's what that is. I'm going to check it with my calculator. I'm going to hit trace, and I'm going to type in 1 over 3 for the 1/3. And what do you know? I get a 0 for y. Okay. The P over Q list, yeah, you're not going to use it every time if it crosses at nice places, but it's very, very useful when you have it crossing at a questionable place, because I can't eyeball the difference between 1/3 and 1/4 on that calculator. There's not much difference in those two values. So that means what I'm going to use now to do my synthetic on this cubic is 1/3. Remember 3, that's a 1. That'd be 0. 0, 27. 1/3 of 27 is 9. And there I have a nice quadratic left over. 3x squared plus 27 is equal to 0. Technically, there's a 0x in the middle there if you want to write it. But, then once we get it down to quadratic, we got all those options about solving quadratics. We got quadratic formula. That's handy. Factoring would be an option. This one doesn't factor really nicely, but it would factor a little bit. But we'd still have to do some work. We also have solving by square roots, which would definitely be that's the way I'm going to do this one, is solving by square roots, because I've only got the x squared left over in there, so I don't have to think about that plain x and dealing with it. So I'm going to solve this by square roots. Yeah, 3x squared is equal to negative 27. I'm going to divide by 3. Negative 9. And then I'm going to take the square root of each side. Don't forget the plus or minus always goes in front of the square root if you put it into the problem. I'm the one that put it in there, so I got to put plus or minus in there. Yeah, plus or minus 3i would be the way that we normally write that. So we have our zeros are x equals negative 2, 1/3, and plus or minus 3i. How many is that? Negative 2, 1/3, positive 3i, negative 3i. That's 4, right? What was the degree of the original polynomial? 4. That should always match. Okay, so your degree should match the number of solutions that you're going to find. Now, what I want you to see here, there's this theorem called the complex conjugate theorem. And what it tells us is that if you've got an imaginary or a complex solution, it'll always be one of them with the plus and one with the minus. They come in pairs. So if they tell you that 3i is a solution to this problem, then so is negative 3i. They come together. Okay, that'll come into play as we build polynomials in just a little bit. Okay, let's look at another one of these and see what we can gather from it. Example B. Again, we're going to find the zeros of a polynomial. So we had x to the 4th, 6x cubed, 2x squared, minus 26x, plus 17. How many times should we have to do synthetic on this one? Why 2? Because it's 4th power, right? And we want to get it down to squared. 4 minus 2 would be 2, right? Whatever the degree of the thing is, if you subtract 2 from it, that'll tell you how many times you need to do synthetic division. out of that. So I know I'm going to do some synthetic. So I'm just going to go ahead and set that up. I just don't know what's going to go on my shelf yet. How am I going to find that? Graph it. Okay, so you graph that equation. X to the fourth. Oops. Plus 6x to the third. 2x squared minus 26x plus 17. It crosses at 1. It bounces off at 1. So what's that tell us? Multiplicity of an even number. So it's either 2 or 4. We know that based on that graph, that it's bouncing off the x-axis at 1. Okay, I'm going to verify that by hitting trace and then typing in a 1 just to make sure that is getting 0. It's not, just almost 0, but it really is 0 on the y. So I know I can use 1 in my synthetic division. I know I can use it at least twice. Okay, not very likely that I would be able to use it 4 times, but I could use it at least twice because of the bouncing off the x-axis. Remember, that means the multiplicity is even if it touches the x-axis and doesn't go through it. So I'm going to put a 1 up there and then run that through with synthetic. What did I do wrong? 9. Oh my gosh. That's fine. There we go. Negative 17. Negative 17. There's a 0. Sorry. All right. So that got us down to a cubic. We know that 1 should work again with synthetic on that polynomial. We don't want to go back to the original because we're trying to make this a smaller polynomial every step. So I'm running the 1 again. And well, it works again. Remainder 0. So we know our zeros over here. X equals 1 with a multiplicity of 2. So that'd be how I'd note that. X equals 1 with a multiplicity of 2. Now that got us down to a quadratic. Now I could take the chance and say, okay, well maybe 1 works 4 times and try to do synthetic again. I'll go ahead and tell you it doesn't work if you do it again. If you have a 0 that's got a higher multiplicity than 1, if you try to run it through what's left over and it doesn't work, then it doesn't have that multiplicity. Okay, so here it worked twice. If I ran a 1 through this, it wouldn't work again. So the multiplicity of the 1 is only works twice. So we have a quadratic left over. We have x squared plus 8x plus 17. And technically that's equal to 0. Okay, so we want to try to solve that. Well, if I think about my ways of solving that, if I think about factoring, is there anything that multiplies to be 17 that adds to be 8? No, so that factoring is not going to work. Quadratic formula is the way that I would do that. I'd almost, anytime I get a trinomial left over there, I'm probably going to do quadratic formula every time anyway. That way I don't waste my time trying to factor. Unless they ask me to write it in factored form, then that's when I would try to factor. But if I'm just asked to find the zeros, once I get it to quadratic, I'm going quadratic formula every time because it's going to work every time if it's a trinomial. If it's just like the example A, I had only the x squared there. Square roots is faster. That's why I do it that way. But quadratic formula would work on that one as well. So x equals negative b plus or minus radical b squared minus 4ac divided by 2a. So that's what we're plugging into. To be negative 8 plus or minus 8 squared minus 4 times 1 times 17 over 2 times 1. And we're going to simplify that and see if we can get an answer. We get negative 8 plus or minus, and then that'd be 64 minus 68. Oh, man, so that's a negative number underneath there. That's a negative 4, really. So negative 8 plus or minus square root of 4 is 2. Should be 2i because it's a negative number over 2. And then I can simplify that a little bit. Yes. So I'm splitting it apart. That'd be negative 4 plus or minus I. So my zeros are 1 with a multiplicity of 2, and then x equals 4 plus or minus I. Those are the zeros of my polynomial. And again, we're getting 2 solutions there from that quadratic formula. You know, they're complex conjugates of one another. One's a plus, one's a minus. That's all that really means. Okay. Not too bad. It's straightforward. That's going to be the style you're going to do about every time. I mean, there's a few exceptions. I don't know if you noticed on the quiz, but most of the first 2 that you were just finding the zeros on, you could factor by grouping. I don't know if anybody noticed that you could do that, but you could. Sometimes you can see that happening, but on these polynomials we've done here, it doesn't happen. So that gets us solving them. Let's talk about building a polynomial given its zeros. All right, so let's look at that. I'll do a couple examples of that and then get out of here. All right. Let's start with one like this form. It's called forming the polynomials, what they say. I call it building. The main thing you got to remember when you're doing this is that conjugate pairs. What that tells us is that if square root of 2 is an answer, then so is negative square root of 2. You get the positive and the negative side of that. With the complex solutions, if they tell us that 4 plus I is a solution, then 4 minus I has to be a solution too. They're going to come in pairs. They won't tell you about both of them most of the time. They'll just say, all right, let's build a polynomial of degree 3. Forming the polynomial, let's say they tell us the degree 3 with zeros, negative 5, and square root of 6. What we know is that negative 5 is a 0. So what's the factor that goes with that? X plus 5. Square root of 6 is a factor, or is a 0. So the factor that goes with it is x minus the square root of 6. But anytime we see that radical or anything with an I in it, we got to know it's got a pair that goes with it. So the other factor that goes with that, x plus the square root of 6. So the 0 they don't tell us about, but we should know it exists, is the negative square root of 6 is the one that they didn't tell us about. Now that's the factored form of that. We want to get it in standard form. Okay, so anytime I've got those conjugate pair pieces there, I'm going to multiply those together first, because that'll get rid of those radicals involved. So I'm going to multiply these two together first. X times x is x squared. I get a negative x radical 6, a positive x radical 6, and then a negative square root of 36 out of that. And then I can simplify that. I've still got the x plus 5 hanging out in the front, but I'm going to simplify before I multiply by x plus 5. This will simplify to be x squared. These guys in the middle are going to cancel out. Minus 6. Square root of 36 is 6, so that's where that's coming from. And now I just got to multiply x plus 5 times that guy. So x times both of those be x cubed minus 6x, and then plus 5x squared minus 30. The only thing left to do is just put it in the right order, which is descending order. X cubed, 5x squared, negative 6x, negative 30. We've built or formed a polynomial given 2 zeros, but we knew there should have been 3 because they told us the degree. They're going to tell you the degree, and they're going to tell you the zeros. What you should know is whatever the degree is should help me know how many zeros exist. Okay, so they gave us 2 zeros. We know there should be 3 because it's a degree 3. All right, those match up. All right, let's look at another one. One with a complex. All right. Say it has a degree. We'll do degree 3 with zeros 5 and 3 minus 2i. So we get a complex going there. What's the zero they didn't tell us about? Yeah, 3 plus 2i, the conjugate pair. Remember, a conjugate just changes the sign in the middle. We've been working with this in Algebra 2 last week or so with conjugate pairs and things. So, all right, so that means I'm going to have, when I go to build my polynomial, I'm going to call this one g of x just because I'm tired of f of x. And let's build the factors. That easy factor is the 5. What factor goes with it? X minus 5. That's the easy one. The other two are not that much more difficult. You just got to know, okay, it's going to be a minus 3 minus radical 2 and then a minus 3 plus radical 2 out of that. So x minus 3 minus 2, or not radical 2, but 2i. And then an x minus 3 plus 2i. Always going to be a minus sign there in front. The only thing that could change that is if that was a negative number and you just put the two negatives together. Now that's pretty ugly looking. Ain't no question. It's pretty ugly. But we can work with it and multiply it out. So we just got to take it a little bit at a time. So obviously I want to multiply these two together first because they both have the I thing in them. All right, so we want to get rid of that for the polynomial. So I'm going to multiply these two together first. All right. And I just do it with distributive property. I think that's the most straightforward and easiest way. You're going to have an IX thing. What should happen if we do everything correctly here is the stuff that has I's should cancel each other out. That's what should happen. Okay, so if you do everything right, there shouldn't be an I left in the problem. For everyone that has a complex or a radical, the I's and the radicals go away if you do it right. Okay, if you got your factors set up right and you did your multiplication correctly, that's what's going to happen. So I'm going to run that x times all of those. So that's going to be x squared minus 3x plus 2ix. And then I'm going to multiply negative 3 times all three of those. So that'd be another negative 3x, and then a positive 9, then a negative 6i. It does get a little long here, but we'll see some stuff go away in just a second. So negative 2i times all of those. So negative 2ix, positive 6i, and negative 4i squared. And then we still have our x minus 5 that we're going to take care of last. We don't have another one, but we've got to remember something about I squared from Algebra 2. It turns into a negative 1. That's what it does. So what we should see here is we got a positive 2ix, and there's the negative 2ix. They cancel each other out. And then we've got a negative 6i and a positive 6i. They're going to cancel each other out. And then this negative 4i squared is really negative 4 times negative 1. So it's really positive 4. And now we can put all our like terms together. We've got x squared, and then we got negative 6x
Would you go ahead and have that 4 to the side?
Yeah, I'd go ahead and say 9 plus 4 is 13. So that big ugly stuff here turns into a nice little trinomial. And that's what should happen. Is it either turns into a trinomial or a binomial in some cases, depending on what this complex thing is. If that was just something with an I, didn't have the 3 plus on it, it's just like 2i, then you're probably going to get a binomial when you simplify there. But it's still the same process. All right, and then the next thing to do is multiply the x minus 5 times the x squared minus 6x plus 13. So I'm just going to run the x through there. X cubed minus 6x squared plus 13x. And then run the negative 5 through there to be negative 5x squared, positive 30x, and then a negative 65. Simplify, write it in descending order. 11x squared, 43x minus 65. So we've built a polynomial using our superb Algebra 1 skills. Other than the I squared, I mean, really it all is just Algebra 1 stuff. It's long, don't get me wrong, and there's a lot of operations there that can make mistakes happen. You just got to be patient and try to do it one piece at a time. Don't try to multiply 2 or 3 things together at once. If you'll do it one at a time, you're going to be fine. It's just going to be it's like anything else. The biggest mistake you're going to make is a sign mistake somewhere along the way, and if you should be able to catch that if the i's don't cancel out and the radicals don't cancel out, something's wrong. Okay, that when you do your multiplication, if that doesn't cancel out, something went wrong. All right, so the practice problems that I could work with, page 363, 7 through 30, and then 31. I don't know why I did that, but let's just use 7 through 40. I don't know why I had 2 sets, 7 through 30 and then 31 through 40. Don't know why I did that, but I had that written down for some reason. So that'll get you 5-3. Again, it's the same stuff. It's just a bit more, the complex solutions in there makes it a little tougher, okay?